Okay, I think we can start. The good news is that it looks like if we end really early, we can go early, and the bus will take us to do the mentoring session by the pool.
No, you are wrong.
Oh, crap. I was hoping I could say that if I get through my presentation really quickly, that actually we can be by the pool earlier. Are you saying that's not true?
It is true. I changed the transcript.
Great.
So, something...
You're our hero, Jean. Okay.
Transfer will be at 4 o'clock.
Excellent. So any time I eliminate here, we can add into the next session. So I don't need to be slow, I can be quick. Right, so I just found this out the other day. I thought it was amazing. 62 people in the world own half the world's wealth. One way of saying it, or same as half the poorest of the world. So while we walk around in the suburbs of very famous football stars and think that actually if everything looks like this in Brazil it must be amazing, we have to keep in mind that actually there are also going to be poor people, and even in Coventry and United Kingdom and all these places. Do you want to look at this? Okay, so I thought I'd run through something that hopefully is a little bit familiar with you, but possibly hasn't really been talked about too much, because I hear a lot of people saying, I'm coming here for collaboration, which is great. And actually, I think that's completely fine. But actually, the original reason we came here together is because we wanted to make some inroads about something that we felt was important. And hopefully you also felt it was important. Let me just remind you what it is. Okay, so why are we here? Well, we're here to discuss the issues around getting microgrids out there. And in particular, that, we know that they seem like a good idea. They would enable, potentially, for lots of people, local control. They would empower the associated communities. They would have control over their heating, their light, and so forth. It would enable local generation, right? Which is important partly because it reduces transmission losses. A lot of the power stations, traditional power stations, are usually far away from the communities that actually use those energies, and there's a transmission loss in getting the stuff to it, the power to them. And then also there's the final thing of local context. There's probably a few more things that are advantages of microgrids, but these are the main things that we felt were important. But it's not so easy. And why isn't it so easy? Because, well, part of the problem is that there is a lack of accessible tools. And one of the things that I feel as a computer scientist, particularly when I talk to people who are non-computer scientists, is sort of a little bit ashamed, because I know that the stuff that I'm developing, that I'm working on, isn't always as accessible as it could be. That it's okay while we've got our PhD students out there twiddling the knobs, but if they left, then the people involved wouldn't necessarily be able to operate. And actually, one of our projects specifically brought that home to us. We tried to get some civil engineers to use our kit without our supervision. It wasn't a complete disaster, but let's just not say too much about that. And then lack of education. So I'm not talking about civil engineers, they're perfectly well educated, but the communities in general, if we want to target particularly remote communities, we can fully expect that they're not going to understand what it is we're doing, that they're not going to even have a clue about the basics of operating a solar panel, let alone anything else. How do we make this obvious to them? So what we thought of doing was, firstly, that it's not a problem that's going to be solved by big business, by the larger industries, by the big six, as somebody mentioned to me this morning, of power companies in the UK, for example. And probably not by governments either. It's not really in their interest. The status quo is okay for them. And rather, we really need to bring together here, actually, experts that are capable in these areas: renewable energy, social sciences, and computing. And I know that we've just had a great big load of computing talks, and all of you social scientists are thinking, well, is this all about computing? We honestly want to say back to you, it's not. And there's going to be lots of, hopefully, things that you can relate to in this talk as well. So our aims in this work are really to make sure that when we do development of wireless systems, that it's informed, right? And it's informed in a way that means that actually it goes towards community-based microgrids and microgeneration. Now, that's largely for a lot of the social scientist type people around the table to come to tell us about how we do that. So I really want your input and questions even. And then we want to find the gaps in the education and find the things that are making it inaccessible in the Brazilian context. And there we want to have our Brazilian partners fully engaged to do that work, to say, what is the Brazilian context actually? Because we don't know. Okay, so finally, and I think this is the last slide, we want to have an impact. And if we do really well, maybe we can do some of the things. And the aim will be overall to empower these communities to be able to run their own community, to run their own microgrid rather, and to control that microgrid, not just to have it sitting there while somebody else comes in occasionally to maintain it, but to be able to control it themselves, to be able to make use of the sustainable renewable energy sources rather than having to rely on fossil fuels, and to reduce their energy costs. So that was extremely quick, so that's really great. I'm working hard towards the swimming pool here. Okay, so I want to tell you about Cogent House. Somebody said, oh, I want to come and see this Cogent House of yours. Actually, it's not actually a house. I'm sorry about that. We didn't think of that when we were naming it. It's really a system of software that was aimed to cope with the problems around monitoring houses with wireless sensors. And we had a particular context in which we developed it, which was we had a client who is Orbit Homes, and they came to us. They're a social housing landlord, and they came to us saying, we want to actually understand a particular building. They were doing a new build of 24 passive house homes, and you've heard Ross talk about this. The main thing about passive house is that it's a technology that's been developed in Germany. It's super insulated homes. They're very efficient, and ultimately the word passive comes from the idea that you wouldn't have to have any heating whatsoever. That in the depths of the UK or German winter, that you wouldn't need to heat it. The person walking around the house generating about 100 watts of heat energy just by being there would be sufficient to keep that house warm. Okay. Actually, I always come to conferences in hot climates and then have no ability to tell people about how important it is to keep warm. Okay, so, but the real question is that passive houses aren't used in the UK generally. Why not? Do they work? Do people really actually need that much insulation? And does it really save them money? So this is a fundamental cost. They wanted to reduce heating costs and reduce fuel poverty, but they weren't really sure whether or not it was going to work, and they wanted some way of finding out, and they actually gave us a really broad brief. They said, just instrument these houses. You decide. And we suggested a few things. Okay, and they also said, well, can you look at CO2 as well? Okay, we'll do CO2. That's a bit tricky, but we can do it. And interestingly enough, I note there that a district heating system was used to supply hot water. So it's supposed to be a really efficient way of doing things. You have a central boiler, it does the hot water for everyone. It's going to be really efficient in principle. Okay, here's the layout of the homes. They're in 3 blocks, 3 little clumps. They tried to get them all facing to the right direction. It wasn't quite possible, but you know, I don't know where south is on this. The idea is to, as much as possible, face south. If you were in the southern hemisphere, maybe in a colder climate, you would want to face north. Okay, so we had 176 nodes. I think we probably had more of that by the end of the project, but lots of nodes, a few servers, lots of homes, some communal areas, and that deployment area. And you've seen this picture of our sensor nodes. I know it's not clear. I've just got one picture of some data I actually took, put this on the slide yesterday, so it's not exactly current, but it's actually from my house. And in a minute I will possibly try and show you some live data so you can see what our system produces. But you'll notice that in this example that it's got only a few small measurement points. And that's because in this particular example there's a reduction protocol being used called edge mining, or SIP we also call it, which basically says, well, I don't really need to know about these points here because they're so predictable from that point there. So it reduces substantially both the amount of data we send over the network and the amount of data we store, because a lot of the data is very redundant, and actually I think that's probably true for most environments. Okay, so I think it was mentioned before actually that we jokingly called this passive house the lava pit, or rather built over a lava pit, because the fundamental difficulty they had is that for a lot of the homes we discovered that the heating was non-functional. And the reason why it hadn't been discovered earlier was because there was self-heating from the district heating system, which had a system of pipes running through the building. It was enough heat being generated, and the insulation was very good, that it would heat the building really nicely. This sort of quite convincing data plot here suggests that this system would stop using energy when the ambient temperature, the outside temperature, was about 50 degrees. Right? So this gas consumption in kilowatt hours is per day. So for 23 homes, one was unoccupied, 23 homes, the average works out to be something like about 26 hours, kilowatt hours per day, just in heating. Just in heating that actually, for some of them, wasn't actually doing anything. Wasn't going into their system at all. And they ended up with temperatures that look like this. So you can see from this that a comfortable temperature we were estimating around here. That would be what you'd want. And by and large, except for this house over here, which was unoccupied, they're uncomfortable, uncomfortably hot. Yeah. And they're uncomfortably hot even in winter. So it's quite striking. The situation or the architecture or anything like that. I want you to understand the problem of getting these projects off the ground. And in particular, with ensuring that they have the right sort of impact. And this should sort of help highlight this issue. So 2011, we had a report out pretty close to the start of the project, indicating that they had a big problem with their heating supply. We gave them graphs in about 10 different formats, and they said, no, we don't quite understand. We went back and revised those graphs and limited them down and finally came up with a way of presenting it to them so that actually they were clear. They're using much more energy than they really need to. And they still didn't understand. And eventually, they understood because they finally started receiving the energy bills. So in 2015, they started work on doing remedial work, and they discovered all these problems about heat transfer units that weren't functioning and hadn't been functioning since the initial install, and so forth. And their reaction really was quietly to shut it all down, because it was a bit of embarrassment by this stage. The house is still there, and they're probably still paying their exceedingly large gas bills. And I'm not too sure how they've managed to transfer some of the ownership of that bill to the tenants, but you know, it's not really a good prognosis, not a good situation to be in, either for the tenants or the landlord. So what's the lesson for us? In particular, what's the lessons that we can possibly share with this group? Well, we need to plan for having an impact. It's no good just saying, okay, well, we're going to do this great wireless sensor network stuff, or we're going to do investigate how communities react to these systems, or actually we're really interested in microgrids, or we want to just put solar panels everywhere. What we really need to do is think about what the long-term impact will be. And basically, think now, is it going to change a company or a government policy? So one of the striking things was to come out of that project and we thought, okay, well, we've worked really hard. We've had this limited impact. We did actually end up getting the people to understand what we were doing and understand the value of it. And yes, we've monitored something carefully. But we also had to compare with other projects which had done simpler things and actually caused policy change. And that was sort of a pause moment for us to say, okay, right, well, maybe we need to think about policy change. We need to think about how this will impact other people's lives earlier on. You know, one of the things through that whole process was ensuring our stakeholders were engaged, you know, and that our voice could be heard. It was quite frustrating at times to be in a meeting with one person pretty much predominantly, and then finding that other sections of the same organisation weren't really talking to them, weren't really liking their ideas, actually had no real stake in your project or the outcomes. Think about a steering group. Seems obvious, but actually it's a wonderful way of getting the stakeholders engaged. They need to be people who are really stakeholders, possibly members of a community that you're targeting, for example. And avoid talking to just one group. So don't get yourself too isolated saying, okay, we'll just talk to government, we'll just talk to industry. And finally, I want to say, make sure the system is easy to use and put it in their hands so that you make sure that they can have the ability to try it out. Now I just have to shout. Oh no, I'm back again. Okay, so when I thought about this presentation, I thought what I really should tell you about is my experience of other Grand Challenge projects, because I think this is in a way a very big challenge. So this is fun. I don't know if I've got an internet connection or really that we really need to see this, but I've put the links in just for your amusement. The first, Robocup is a fantastic idea. Some researchers came up with the idea that we could really progress robotic research if we could get people to try it out in competition with each other. So they set a grand challenge, and the vision was to have a team of robots that would play and possibly win against a human team by 2050, right? Specific date, 2050. They're going to have a human team, and that's their vision. They're going to be able to play against a human team, rather. So you may note that if you look on the list of people who are currently working on autonomous cars at places like CMU and Google, that some of the key people have also done their basic work, the fundamental work that led to their understanding of how to do this stuff in Robocup. So Robocup was wonderful from a perspective, not just because it's got this wonderful vision, but also because it's going to have a real impact potentially on how we live our lives. The potential for autonomous cars could be quite amazing. Might cut accidents completely. Some people think not, but it might. And it might change the way we think about even owning a car. You might stop owning a car and just have an Uber car come to your door every morning at the right time. So the competition format really accelerated the progress, and I think that's the main thing I liked about it, that actually it allowed people to say, this is my work, this is your work, how do the two really compare? How are we actually doing? So in this, I don't know, I'm guessing that it would still be possible for, say, wireless sensor network guys to share their work, but in a sort of competitive environment by having trials with participants saying, you go and deploy this, how good is it? Did we make any advancement towards that key idea of getting things into other people's hands? Okay. And I haven't got a watch, but I'm pretty sure I'm really doing well for time. So it's good. So the other big project that I've been involved with is the Auto ID Centre, and that started in about 1999. It eventually, by the end of its project, involved about 100 sponsors. They're all big industry, so for the people here who like steering away from big industry, perhaps you'll say, it was companies like Walmart and Procter & Gamble. But they were very interested in revolutionising their supply chain, which they saw as a big problem. And they'd had recent experience with the electronic theft protection tags, which ended up with 2 different standards coming from different companies. And then, no one was really clear on which standard to use, and it was just caused a whole lot of hassle. You couldn't take a product from one store, move it to a different store, and hope that it would still work. So they were thinking, well, let's try and have a way of standardizing on a way of doing these things based on the best of the state of the art. How do we get there? And they had some great impact, and it's sort of impact that we're seeing today. The reason why we have the term IoT is because one of the Auto ID Centre guys came up with it. Okay, so you may think this is the end of my slide, but it's actually questions for you. So what I want you to think about now is, what is the vision? We've talked about this, we've got proposal ideas there, but what is your vision? What is your vision for this project? What should we be aiming to do? By what date? How do we make sure we're engaging the stakeholders, the right stakeholders preferably? And what are the roadblocks to success? What are the things that are really standing in our way? So I'm hoping that you're going to answer these questions throughout the week. I'm hoping. Now, I haven't talked any technical stuff. Do I still have a little bit of time? There are still some wireless sensor network guys. Oh, you can do it for me, can't you? Yeah. Okay, so this is based on some work that I did some time ago, but I'm showing it because I think it's useful to get an idea of how we're all thinking about this problem, because we've got people from different sort of communities here, and I just want to try and tell you what my view is. One of the classic problems that you get into when you go and talk to other people working on other wireless sensors is that they're talking about a different bit of hardware with different sensor configurations. They've written there's all in a language that you're not familiar with, and it's really hard to actually contribute to them or for their work to contribute to yours. So this is actually not an uncommon problem in computer science, and a nice way of going about solving that problem is to come up with design patterns, things that are telling you about the way you're going to do something rather than exactly how to implement it. It's sort of just structuring the work a little bit. So in the top part, we've got sensing. Now this is talking about a single device. So it's sort of going around a loop here of doing some stuff. And I'll just go through briefly what things you're likely to want to do in this circuit. And hopefully for those people who aren't wireless sensing guys, I'll do it in a high-level view so it won't be too difficult for you to understand. Okay, so the first thing that you probably want to do when you receive a bit of sensor information is to filter it. Raw sensor information is not necessarily a good reflection of the true state of the environment. You get small fluctuations that are not anything to do with the real value. I've got an example down here. Right, you get this sort of data. Actually, there's quantization noise here as well, but this is the sort of thing that you get. It's a jittering around the place. And the blue line that I've just traced here is just an example filter that you might have. Okay, I have to go back. Right. So what we can do is we can say, okay, well, these are the key things you need to know about when you're considering doing a filter. Okay, this is why. Because you want to reduce noise, you want to summarize into a sensory chunk, you want to infer the state. The approach is going to be potentially involving partitioning into external, internal, and also you might have separate filters for uncorrelated data. And you can think of a filter looking like this. I'm coming on and off. It sort of works. Okay, so again, I don't need to go into the detail here, but this just gives you an idea, an overview of what this component looks like. It's got some inputs, some outputs, and then it reuses some of the process of the data that it had from last time. Okay, so the next step is often doing event detection. And you can combine that with filters because you don't want to detect these small fluctuations as being important events. They're usually not. The slippery slope problem is if you look at the change from last time, the change may be very large or maybe small, but how do you know what the true state is? So an event detector is a good way of thinking about the problem so that you avoid a slippery slope. Basically, instead of looking at, oh, I've just changed a little bit, I've just changed a little bit, I've just changed a little bit, and assuming that there's no event, you look at how you've changed overall in terms of your overall state. So we also realized that once you do event detection that you might have very infrequent messages. We had an example before where we ended up with only 13 or so messages a year. And that means that you often don't know whether or not you've got working wireless sensors, whether the batteries have died or the hardware has failed in some way or they've just been taken away by somebody. And to help with that, you can have a heartbeat. You also need to think about what happens if a message is lost and how do you cater for that. So I won't go through the diagram. So, and this is what we've sort of started coming across more recently is the need for buffering and storing some information on the node just in case you have a long period where you don't have access to transmit your data out. It's basically about getting these nodes to work semi-autonomously. Okay, and then finally, you don't want your nodes listening all the time. They don't want to be chewing their radio all the time, so you need to take a technique like one of these approaches to basically not listen all the time. The example I give here is that ordinarily you'd be listening all through this, and that's chewing your power over time. But actually, possibly you can get rid of this and just only listen at particular times. And there's a couple of strategies for doing this. And it means that you really extend the lifetime of your nodes so that they last months instead of half an hour. Okay, and finally you need a way of putting this all together so that it can be done without too much complexity. So the internal parts of this operating system, if you like, for very small wireless nodes can be complicated. It's not Windows running, it's not a Linux system that's running there, it's much simpler, and so you might need a way of dealing with that. Okay, so that's pretty much the end of my talk. I wanted to add in the design patterns because I thought it would round out the idea of where we're coming from. I hope that's interesting to you who understood it. I hope it's not too difficult for those who didn't. But I think broadly speaking, I think my main point of this thing was to get you thinking about those questions about what we're trying to get to here and what our vision should be. Okay, thank you very much.
Thank you for the talk. Maybe that may be a dumb question, but I would like to ask you anyway. How do you evaluate that kind of pattern?
I think the same problem. I think the same problem occurs for all design patterns for object-oriented systems, and that they have no way of really evaluating them, other than throwing them out into the discipline and saying, here they are, here's what we thought were good, and we had good reason for those ideas, refine them, change them. But yes, it's a very good question. There's no easy way of evaluating such a thing. Yeah. Did you have a question?
It was so beautiful the way you put together all this big picture through which students have to go through before going into the field. Whenever we have a new project, the students get data and they start, then they realize, well, this doesn't look like the other one. I don't know whether this is relevant. Today the link failed. So it looks like they have to learn everything again from scratch. And at most, they look to an old project and say, well, they use a common filter, let's copy that, but they don't know why. Do you think it would be possible nowadays to classify a dozen or 100 of cyber-physical systems and make suggestions for what kind of interference usually come out of this kind of system, what kind of filter is good for this system, what is the duty cycle that is optimal for this kind of, just as a hint to prevent students going through all that painstaking learning of this?
So I wish there was an easy answer to that, because we continually go through that problem again and again. And I think when we changed to doing our work on buildings monitoring, we had strain gauges. Strain gauges operating on a different time scale than temperature sensors, and you need to think about the data slightly differently, and so that there are going to be similarities to that system, but also dramatic differences. So that's why I was really suggesting having a design pattern approach, which allowed you to at least try to formulate, if you've got this sort of situation, try this. And we've done some work towards that formulation, but I think we're really open to having more work being done and more discussion with other people about it. So, but no exact numbers because, you know, when is the right time to use a Kalman filter? Sometimes the Kalman filter will be too mathematically complex for your tiny little node to do. Sometimes you're going to be exporting the data back to a larger server and then you can do a Kalman filter maybe a lot easier. So yeah, it's a good question. There's no right answer, I think. Yeah. Yeah. I think you know, even this starting point is useful to them because then they know the cycle of things that they're probably going to need to do, and then yeah, they can miss a step out. You know, maybe they don't have to have a priority buffer. Maybe they don't actually want to filter the data this time, but they can at least think about, oh yeah, actually, I'm going to go around this cycle, but which of these components should I be using? Yep. Any other questions? So I hope you at least give me some applause for actually ending like 20 minutes early.